pushed back by these fantastic results. To detect planets, you have to be able to first suppress the light of the parent star. First you want to have it corrected with adaptive optics so it's as close as possible to a diffraction limited image. Then you suppress the star light with techniques like coronagraphs, etc. And then you get images where objects of even 10 to the minus 9 and 10 to the minus 10 appear visible in our simulations. Of course, real life is slightly more complicated, but this is at least promising. And the point is that there are techniques that allow you to understand better or to improve your capabilities of going down in contrast, and this is an example of one. You can see the arrow points towards a planet in a system where you cannot distinguish the planet from the speckles that remain after the suppression of the light from the parent star. However, if you take images at different wavelengths, what happens is that the speckle will have a distribution that depends on the wavelength, while the planet will not. And so, in the end, there are ways to gain information from this wavelength dependency of the speckle pattern. You can do it the other way around. You block the speckles and the planet starts moving. And in fact, this is very interesting. Those of you that have very good eyes will have noticed that there are two planets in this picture, and these can be put up and discovered with these techniques. Here is the result of a study with for a planet finder instrument for the extremely large European extremely large telescope, which has the ability to go down to 10 to the minus 9, maybe even 10 to the minus 10 at a certain distance from the parent star in terms of contrast. Similar analyses have been made for the other telescopes. The planet finder instrument for TMT will also be very powerful in searching for these planets. And this telescope will also characterize the atmosphere of these planets in various ways, either through looking at them, at these planets during their transit in front of the parent star, or by, if they are bright enough, making directly spectroscopy on their images in these integral field units that are used to detect them. In the nearby universe, the big advantage that these telescopes will have is to work at the diffraction limit, to be able to separate out stars in galaxies that are several dozens of megaparsecs away. And this will be a way to understand the evolution of the stellar history of the universe. This is an important topic for astronomers to try to understand how the star formation history of the universe has evolved with time. And there are two ways. One is to look at objects that are very, very far, and the other is to look at objects that have stars that were born a long time ago, and try to understand how this star formation history came from the past to the present. And we call that stellar archaeology, and this is something that is a very strong case for the extremely large telescopes, because there are kinds of galaxies, like elliptical galaxies, where we do not have yet a clear indication or clear understanding of the distribution of stellar populations there. Further out, the study of merging galaxies is also something that is important for us to understand, because they trigger very often episodes of star formation. And of course, by being able to go to higher and higher resolution, this will allow us to understand better what the merging process is to create larger galaxies. And it's important to understand that these telescopes, having a very large collecting area, will be able to make very deep spectroscopy of many of these objects far in the universe. And some of the telescopes are a clear plan to go also into the blue area of the spectrum that allows us to probe better the distribution of objects in the space of the redshifts. Let me just go to the further universe and the cosmology, that is also a very important and driving science case for extremely large telescopes. Today, our understanding of how cosmology, how the universe has evolved is based mainly on three pillars. The Hubble diagram for supernovae that shows that the expansion of the universe is now accelerating. The information that we gather of the origin of the beginning of the universe through the cosmic microwave background and the distribution of galaxies. And all this gives us a picture of the universe in which dark matter is distributed in curtains and filaments, and acts as a seed for the formation of galaxies and the formation and the collection of neutral hydrogen that then absorbs the light from the most distant objects. And this is something that we would like to understand better. The universe is composed mostly of things that we do not understand very much about. They call them dark because they don't emit light and because we don't understand them. And although we might have some hope that particle physics might help us shed some light on the dark matter itself, the dark energy is still a tantalizing riddle for us, one that we would like to understand better. And one of the things that we can do is to try to determine its equation of state, as the astronomers say. In other words, we have a chance with these very large telescopes to actually measure this acceleration of the expansion of the universe, catching it, if you will, in the act. And the way you do this is very simple, in principle. You take a measurement of something that moves away from you very fast, and in our case, we select to observe many of these objects. These are this is the gas associated with those filaments that we have seen before that absorbs the light from very far objects, and they are at different positions in the universe, and so they are expanding at different velocities, and so you get many observations of many velocities. You wait some time and observe again. And if the velocities have changed, you have a variation of velocity over a variation of time, which by definition is an acceleration. You will be able to actually see the universe accelerate in real time. This is something that today we know by what we call geometrical methods. We compare things that we believe are the same brightness at a certain distance and at another distance, and we find out that the ratios are different from what we expect from their ratios of distances, and we decide that something must have either decelerated or accelerated the expansion of the universe to allow us to make this comparison. This is a method that is direct, is dynamic. You measure velocity today, you wait a little bit, you make another measurement, and you find out if there is an acceleration. Now, this example that I've just shown you is quite interesting, but of course requires a large delta time to be visible the way I've just shown it to you. However, what is interesting is that if you look at the y-axis of this plot, you find out that these measurements, the measurement that we are trying to make, are of a variation in velocity, which is of the order of 1 to 2 centimeters per second per year. And this is something that is equivalent to measuring this variation in velocity on objects that are half or 3/4 of the size of the universe away and are moving away from you at a very large fraction of the speed of light. And still, this is something that is made possible by the extremely large telescopes. We will have to have spectrographs with accuracies and stabilities of the order of centimeters per second over several years, because the observations that we need to do to get that particular plot will take about 20 years. But this is the first time that we can make a sort of physical experiment with our telescopes to actually probe in a direct way a dynamical property of the universe. There are many other cases. The study of black holes, both in our galaxy and in other galaxies, will provide us ways to test general relativity theory, and this is something that it's a very exciting and important science case for most, in fact for all of the extremely large telescopes. The fact that we have a very high resolving power in terms of spatial resolution, and also a very high collecting area, allows us, in fact, to go and probe deeply into the nuclei of galaxies that have no external indication that black holes are present, but we will be able to find out whether this, one of the hypothesis is that essentially every galaxy has a black hole in the center, whether this is true or not. We'll be able to test whether the cosmological constants actually vary with time, something that has been claimed at various levels of confidence on several occasions, and here we will gain factors 100 to thousands in terms of the accuracy and the stability of the observation that we will be able to do. The early universe will essentially be made up of the main components that were available at the time, which is hydrogen and helium. As you have seen, all the hydrogen between us and the beginning of the universe is enough to absorb all the emission that comes from most of the objects at those times. But the helium is on the longer wavelength of the main absorption of hydrogen, which means that we will be able to actually see all these objects in their helium lines. And this is very interesting, at the same time very exciting, because it allows us to catch the first formation of stars, the first star-forming units, if you want, of the universe in the act of creating their stars. I wanted to finish just saying that all these scientific cases are what drive the requirements for our telescopes, the requirement of sensitivity, the requirement of high spatial resolution, the requirement of depth, which when we are pessimistic we call the confusion, which is our ability to separate stars in areas where there are many stars. And here is an example of where various telescopes can go into M87, one of the closest elliptical galaxies, and you can see that the ELTs can go well inside the blue radius, which is the effective radius of that galaxy, so be able to probe inside the dynamical, most important part of that galaxy. So the summary of my talk is that as far as we know today, there are a number of fundamental questions that drive the LT requirements. I go from if there is, what is the nature of dark matter, the nature of dark energy, to the, if you want, very fundamental question on whether life does exist elsewhere in the universe. So, thank you very much, and I'll finish here.